All right, hello and welcome. This is the Sagnac effect linearized by Ruyong Wang. So what Wang points out here is that the circular equation given to derive the Sagnac effect, delta t is equal to 4 omega a divided by c squared, is the same as delta t is equal to 2 vl over c squared. And what this means is for the circular equation, the fringe shift predicted is 4 times the rotational speed of the device times the area of the device, or the length that the light has to travel, essentially, right? So if you have a setup where you have 3 mirrors or 4 mirrors, it's going to be the total length that light has to travel before it hits the uh, what is it called, the detector for the fringe pattern, right? So that total length, and then the linear effect is also the same thing here, but just slightly different. So we got your fringe shift amount of fringe predicted is equal to 2 times the velocity of the device, or whatever's in motion, and then the length of the device as well. So, or the length of the fiber optic cable, right? So in a fiber optic gyro, say you have 1,000 meter cable, you would wrap that around in a spool or whatever, and that 1,000 meters would be your area. So in the same respect, just whatever the linear length of whatever you're using, it be fiber optic or laser, it'll be the length that the light has to travel, and that the fringe shift pattern is going to be proportional to the velocity. Now, this right here is the angular velocity equation noted by your boy Omega here. So this is specifically the way that they would account for the Sagnac effect since 19 or whenever this equation was derived. But yeah, this is how they've accounted for it, since 1913, right? Or whenever this one came out specifically. But anyway, Wang in 2004 did this experiment, and he came up with this linearization equation, and he actually derives the circular effect and vice versa from this is interchangeable, essentially, is what Wang shows. And there in that he shows that the Sagnac effect is not due to angular rotation. It is in fact directional dependent. So you get the benefit of speed of light going faster east to west when you're propagating east to west. When you're propagating west to east, the light travels faster, slower. It has nothing to do with the rotation of the Earth or the rotation of the device. The effect was linearized and shown to be due to the velocity of the recipient, or of the observer, right? So what I'm going to pull up now, if I can figure out how to close presentation mode here, is this from the GPS paper. So this is in reference to the example Wang gives of the stationary receiver R1 and the moving receiver R2, and they're going to these two gentlemen are going to get a GPS signal from a stationary or moving receiver, doesn't matter. And even though that the time that they get these is going to be the same, I'm sorry, that the distance is the same, the time that they get the signal is going to be different. How could that be? Well, turns out that the time delay is proportional to the velocity of the receiver, right? So let's see. Contrary to the appearance of the range measurement equation, the speed of the receiver v does not appear explicitly in the speed. The speed of the receiver is implied in the definition of the position of the receiver, i.e., position of the receiver at reception time. So remember, the range measurement equation is a time, or is based on a time interval system for GPS. So they're measuring this delay, and then they're referencing it with GPS's timestamp, right? So they're saying you were here at this specific spot in the coordinate system when this signal was sent, and then X amount of time passed, and then now the signal was received at this particular spot at this particular time, and now we're going to take that difference in time and multiply that by c to derive the distance between the location that the signal was sent and the location that the signal was received. So even though these two are in the same spot, this guy gets his information slightly or at a slight delay proportional to his velocity. Now, if you remember back to the postulates of special relativity, that's not supposed to be a factor. And on top of that, the Sagnac effect itself isn't due to angular rotation. So the effect that's causing this variance in speed here, we can conclude from Wang's experiments and math that it is not due to any sort of rotation on the Earth or any sort of rotation of a device or any sort of anything like that. And I think that should help clarify the position a little bit and get you started on what's going on with everything.